My name is Rishi. I'm studying in Sri Venkateswara College of Engineering, Bangalore, class ISC, third sem. My USN is 1VE23IS042. Today's topic we gonna cover is direct memory access from the subject DDCU. Direct memory access. Direct memory access DMA is a powerful technique that allows peripheral devices to directly access the system's main memory without involving the CPU. What is DMA? Direct memory access is a technique that allows peripheral devices to read or write data directly to from main memory without involving the CPU. CPU offload. This frees the CPU from handling data transfer, allowing it to focus on other tasks. Efficiency. DMA significantly improves data transfer speed performance. How does DMA work? Device request. A peripheral device requests a DMA transfer by sending a request to the DMA controller. DMA controller. The DMA controller receives the request, sets up the transfer parameters, and takes control of the memory bus. Data transfer. The DMA controller directly transfers data between the device and memory without CPU involvement. Advantages of DMA: increased throughput, the reduced CPU overhead, improved system performance. Increased throughput. DMA allows for continuous data transfer without CPU intervention, resulting in higher data throughput. Reduced CPU overhead. DMA frees the CPU from managing data transfers, enabling it to focus on other computationally intensive tasks. Improved system performance. By offloading data transfer, DMA enhances overall system performance and responsiveness. Disadvantages of DMA: memory conflicts, complexity, security concerns. Memory conflicts. DMA transfers can potentially conflict with the CPU's access to memory, leading to performance issues. Complexity. Implementing and managing DMA can be complex, requiring careful configuration and synchronization. Security concerns. DMA transfers can potentially be exploited by gain unauthorized access to system memory. DMA is a method that allows peripherals to access the main memory of a computer without involving the CPU. Complex hardware design. Implementing DMA requires additional hardware like DMA controller, which increases the complexity and cost of the system. Potential data conflicts. DMA can cause conflicts between the CPU and peripherals if both attempt to access memory simultaneously, leading to potential system performance issues. Limited number of DMA channels. System typically have a fixed number of DMA channels. If all are in use, additional peripherals requiring DMA will have to wait or use CPU-based data transfers. Memory access latency for the CPU. While the DMA controller accesses memory, the CPU may have to wait, resulting in increased latency for the CPU's operation. Interrupt overhead, compatibility issues, debugging complexity, power consumption. These are the disadvantages of DMA. DMA modes: burst, cyclic, and demand. Burst transfers a block of data in a single continuous burst. Cyclic transfers data in a repetitive cycle, usually for devices like hard drives. Demand transfers data on demand as requested. DMA controller. DMA controller manages and orchestrates DMA transfers between devices and memory. Transfer parameters. It sets up the transfer parameters such as source and destination addresses, data size and mode, memory access. The DMAC takes control of the memory bus to facilitate direct data transfer. DMA channels and prioritization. DMA channels. DMAC often have multiple channels to handle simultaneous data transfers from different devices. Priority levels. Channels can be assigned priority levels to ensure that critical transfers are handled promptly. Channel management. The DMAC manages channel allocation, optimize data flow. DMA applications. Disk input and output. DMA is extensively used in hardware drive controllers for efficient data transfers. Network communication. DMA is essential for high-speed network transfers, offloading data packets from the CPU. Graphic processing. DMA plays a crucial role in graphics card for fast data transfer. Data storage devices, hard drives and solid state drives, optical drives, networking, network interface cards. DMA transfer data packets between memory and the network without CPU overhead. Multimedia applications, audio processing, video streaming, gaming consoles. Embedded systems, microcontrollers, IoT devices. Communication systems, serial interfaces. DMA is employed in SPI, I2C, or UART to handle data transmission at high speeds. 5G and wireless systems, graphics processing, robotics and automation, sensor data acquisition. DMA transfer sensor data for processing in real time without CPU intervention. Motor control systems, industrial applications, real time data logging, programmable logic controllers, medical devices, imaging systems. DMA handles large amount of data from devices like MRIs and CT scans. Patient monitoring transfers vital sign data from sensor to processing units efficiently. Autonomous systems, automotive systems, drones handles data transfer from camera, sensor and navigation systems. Conclusion and key takeaways. Performance boost. DMA significantly enhances data transfer speeds and improves overall system performance. CPU offload. DMA frees the CPU from managing data transfer, allowing it to focus on more complex tasks. Essential for modern systems. DMA is a fundamental technology used in various peripherals, enabling high performance computing. Improved efficiency. DMA accelerates data transfer processes by passing the CPU, freeing it for other tasks. Reduced CPU overhead. CPU involvement in repetitive high volume data transfer is minimized, leading to better multitasking capabilities. Hardware requirements. DMA requires a dedicated controller and involves increased complexity in system design. Modes of operation. Modes like burst, cycle, stealing, and transparent ensure flexibility for various use cases. Broad applications widely used in storage devices, networking, graphics, multimedia, robotics, and real time embedded systems. Potential drawbacks. Issues like memory access conflicts, limited DMA channels, and debugging challenges need to be addressed during implementation. Future potential. DMA continues to evolve, playing a key role in high-speed and real-time systems like AI, IoT, and advanced communication systems. DMA is a cornerstone technology for modern systems, bridging the gap between high-speed peripherals and memory while ensuring efficient resource utilization. Thank you. Please like, share, and subscribe.